Hi, welcome back to Math 112, Elementary Functions. Today we're going to talk about modeling with trigonometric functions, and we've already been doing some of this. We did this when we talked about how long the rider on the London Eye was going to be over 100 meters. And we've done some examples with temperature during the day. We're just going to do a few more examples, so really there won't be anything new here, just applications. So let's talk first about whenever we have a right triangle, for any triangle, but especially for right triangles, we only need two pieces of information beyond the fact that it's a right triangle in order to know everything that we need to know about that triangle. So we know that this is a right angle. We know that one leg is 5 units long and the other leg is 7 units long. That's enough for us to find these angles, and in fact we could find the length of the hypotenuse as well. A couple of different ways we can go about doing this. Probably the most straightforward is to go ahead and find the length of the hypotenuse, and we can use that by using our good old friend, the Pythagorean theorem. You will find the Pythagorean theorem is the key to the universe as far as trigonometry is concerned. So the Pythagorean theorem tells me that if I label this side C, C squared equals 5 squared plus 7 squared, or, let's open up my calculator here. That means C is going to be the square root of 25 plus 49. Which is the square root of 74. Now, what goes into 74? Well, we know 2 goes into 74, 37 times, so that does not simplify. So we're just going to call this the square root of 74. This is one way to do it, and then we could use sine and cosine. So we could say what angle. So we know that theta then would be, which I'm looking for cosine, so SOHCAHTOA. So the TOA, sine is opposite over hypotenuse, so theta will be the inverse sine of 7 over square root 74. Which I can get from my calculator. A note on calculators, be sure you know which mode your calculator is in. If it is in radians, it will give you your inverse sine, your angles as radians. If it's degrees, it'll give you degrees, but it's important that you know which one you're getting. If you're unsure, you can always test using a value that you know. Like you know what the tangent of 45 degrees is. It's 1. So if you put in arctan 1 and your calculator gives you back 45, you know you're in degrees. So this tells me that theta is, you can also tell by the size of the numbers, your degree numbers are going to be bigger. So 54.46 degrees based on this. We can get phi, which is my other angle, and we can get it a couple of different ways. We could use the inverse cosine of 7 over root 74, or we could use the inverse sine of 5 over root 74. I'm going to show you another way to do this here in a second without finding, it does not involve finding the hypotenuse. The other thing we could do once we had the first angle What do we know about the sum of the degrees of the angles in any triangle? Add that up to 180, so we could always use that back to find our missing angle. All right, suppose I didn't want to find the hypotenuse. What else could I do? Well, I could use the fact that the tangent of B is equal to 5/7. And so then B would be arctan, or the inverse tangent of 5/7, which again gives me 35.54 degrees. Same answer, because remember that the tangent is equal to the opposite over the hypotenuse. Okay? So the point I'm making here is if you know any two pieces of information about any right triangle, then you can find all the rest of it. You know you've got a right triangle and you need any two legs or any leg and any angle or any two angles, and then you can find, well, you gotta have at least one leg. Then you can find all of the missing information. Okay. Another example. We've got a plane right here heading to a point that is 500 miles north and 200 miles east of its current location. And we want to know at what angle should the plane be headed. Well, we know that the tangent of that angle theta is equal to the length of the side opposite that angle divided by the length of the side adjacent that angle. So that means that theta will be equal to the inverse tangent of 500 over 200, or we can just write that out. Use your calculator, although that might be a known value. No, it's not. And we get 68.2 degrees. Okay? There's really not much rocket science here. This is all stuff we already know. Let's suppose you have always wanted a drafting table and you decided to build one. And you decide to build one that is 4 feet deep, and you want the back of your drafting table. Drafting tables are always angled because it's easier to draw. You want it to be a half foot higher than the front. In order to put this thing together tightly, you need to know what angle to cut your legs at. So you're going to cut them at some angle here. Well, this angle right in here is the same as this angle. So what we have is a right triangle with a vertical leg of 1/2 and a hypotenuse of 4. And I want to know this angle. What do I know? Well, I know that the sine of any angle, we'll call this guy alpha, is equal to the length of the side opposite, so that's 1/2 foot, divided by the hypotenuse, which is 4 feet. So my angle will be the inverse sine of 1/2 divided by 4 is going to be 1/8. Again, use my calculator. And we get that that angle is actually not very big. It's only 7.18. Seems like it should be more, doesn't it? That's not. Okay. All right. Here's another example. We've got a point, 3, 4, and I want to rotate it counterclockwise 20 degrees. What are the coordinates of my new point? This one requires a little bit more effort, two-step process. The first thing we want to do is find this alpha angle, that angle alpha. And how do we do that? Well, remember that if I've got a circle centered at the origin, the xy coordinates, the coordinates of any point on the circle, are equal to r cosine alpha times r, or sorry, not times, comma, sine alpha. So the x-coordinate gives me the cosine of this angle, the y-coordinate gives me the sine of this angle. We need the radius. You can use the Pythagorean theorem to get it, but I happen to know that a 3, 4, 5 right triangle, so this side is 3, this side is 4. So for any right triangle where you've got one leg is 3, the other leg is 4, the hypotenuse is going to be 5. Pythagorean theorem will prove that to you. So now I can find that alpha, that angle alpha. Okay. And we'll use the inverse sine of the y-coordinate now. Now, it's not just y, it's actually y over r. Okay. So alpha is, oh, we liking this number today, 53.13 degrees. Excuse me. But now I'd increase that angle by 20 degrees. So my new angle beta is actually that angle plus 20, or 73.13 degrees. But I can get my xy coordinates now, because x is r cosine beta, or 5 times the cosine of 73.13. Or 1.45. Does that make sense? That my x would be smaller? Yeah. I moved from this point here to this point here, so I'm closer to the y-axis. So x is smaller. But y should be bigger, right? Let's check it. Y is going to be r sine beta, which is 5 times the sine of 73.13 degrees. Which sure enough gives me 4.78. So my coordinates of my new point, of my point that is rotated 20 degrees from the point 34, are 1.45 and 4.78. And if you're wondering where you would ever use this, if you do any CNC manufacturing, you have to tell the computer where to drill or cut. So suppose you wanted to drill holes at 20 degrees around a circle that was 5 inches in radius. You would need to tell it to drill at the point. It has to have coordinates, so it would mean coordinates 3, 4, 1, 2. You get the idea. These are actual this is actually an application. It's not an esoteric thing. All right, let's try another one. The hours of daylight in Los Angeles oscillate from a low of 10 hours in January to 14 hours in July. How many months of the year are there more than 13 hours of daylight? Maybe you're trying to plant a garden and you want to know what you're growing. If you just really don't like short days. Let's figure this out. Now, so let's think about this. We've got daylight, And we know it starts in January. And I only have 10 hours a day. But then it slowly increases until I get to July. And there are 13 hours of daylight. What happens in July? Well, it starts decreasing again. Yep. So this is, we know the days are shortest in December. What's this look like? Kind of almost looks like the cosine, doesn't it? If we make January be 0, and December would be month 12. So cosine, it's upside down, so but it could be an inverted cosine, so off to negative something times the cosine of something times x, where x is the months. So month would be here. So this would be t of x or h of x. How are we going to figure all this out? Oh, and there's probably going to be a vertical shift here. So we'll say plus. We don't need a horizontal shift because our minimum is right here at 0. So if we use an inverted cosine, we don't need to worry about a horizontal shift. But what do we need? We need a midpoint, right? How do we get that? Whoops, not 13. 14 hours. What's my midpoint? My midline. Well, it's halfway between 20 and 14, so that's going to be 12. My period, this thing looks like a cosine that's got a period. Of 12. We know how to get to B then. B is, so this will equal 2 pi over B. So B is going to be 12 divided by, oops, I got that upside. That's wrong. Dividing here. No, I was right the first time. This is wrong. B is 2 pi over 12, or pi over 6. So this is pi over 6. My k is just the position of my midline, which is 12. How do I get A? Well, remember that cosine normally oscillates between 1 and negative 1. So it's got an amplitude of 1. I've been saying that wrong for a while. The amplitude is actually half of the distance from peak to valley. So the amplitude is the distance from the midline to the peak, or the midline to the valley. So this has got an amplitude of 2. Where'd my pen go? There it is. So this is 2. So my function is the hours of daylight as a function of months is negative 2 times the cosine of pi over 6x plus 12. But the question actually asks, how many months of the year are there more hours, more than 13 hours of daylight? So let's take a look at a better graph. Oh, but I had a decimals. I don't have a decimals. Okay, let's see. But I have this too many windows open. Let's take a look at those ones, and let's just graph that function real quick. Yeah, my internet at home is awful. So I've got y equals negative 2 times the cosine of pi over 6. plus 12. Whoops, and I need an X. There we go. Oh, clear parent. Okay, let's see if that looks right. Does that look right? Yeah. System projector mode, so you can see more easily. Okay, so we oscillate between 10 and 14, and we repeat. So this is January, December would be out here at 12. So yes, we're good. Now let's look at what we care about. What we care about is how many months the temperature is greater than 13. I'm going to limit myself. So what I care about is this point here and this point here. It does most gives me the answer, right? We get 13 hours of daylight in month 4, which is April, and we keep it until August, which is month 8. So, but let's look at how we would actually solve this. We know the answers now. We know that my maximum is going to be between these and not somewhere else, like on the outside. So let's erase my scribbling here and actually solve this analytically instead of just relying on our graph. Actually understand what we're doing. Erase all my ink, start over. Okay, so my function is that my hours of daylight is equal to -2 as the cosine of pi over 6 times x plus 12. Now what I want to know is where is that equal to 13? So we'll say 13 equals -2 times the cosine pi over 6 plus 12. Isolate the trigonometric function and we get 1 equals -2 times the cosine pi over 6x. Divide through by 2, -1/2 equals cosine pi over 6 times x. Okay, which angles have cosine of -1/2? 120. It's one of them. So 120 is going to equal, oh, wait, what's my problem here? Well, I gave you the answer in degrees. I need it in radians. How do I know that? I knew that because of the pi. Yeah. All right. So what is that? Do they know? All right, I gotta confess, I'm not sure either. So let me look. Let's find our unit circle. Yeah, let's see. Where am I going to find my unit circle? I know, Google knows. I'm drawing a blank today. Memorize that unit circle so you don't look foolish like me. Look up the unit circle. Okay. Angles with cosine of -1/2 are seven pi over 6 and 2 pi over 3. So that means that 7 pi over 6 equals pi over 6x. Or 2 pi over 3 equals pi over 6x. So I can look at that. Cosine negative 1/2 2 pi over 3 and 4 pi over 3. That's wrong. Remember that the cosine comes from the x coordinate. Okay, we solve this and we'll get pi x equals 8 or x equals 4, which is just exactly what we thought. So we get more than 13 hours of daylight between April and August. So that's actually, yes. So 4 months in a year. Okay. And I do believe we've got one more, but it's pretty much the same thing. So I am going to leave this for your enjoyment. If you have any questions, post on the forum or meet me in the scheduled tutoring conference, the scheduled web conference, and I will talk to you all again soon.